Wie mache ich hier weiter mit dem PowerPoint?
Okay, Linus, floor is yours.
Not hiermit nicht.
And wait for the 1400 and we can start.
Yep.
Womit? Oh, la, la. Okay.
Okay, so hello everyone.
Hiermit, ne? Okay.
Welcome to this first afternoon session. Today we have our next plenary lecture. Actually, a lecture which was supposed to take place last year around the same time, but it was canceled the last minute. So we are very happy that Klaus-Dieter Kreuer agreed to transfer his presentation and make his visit virtual to this year's conference. So a little bit about our speaker today. So Klaus-Dieter Kreuer received his diploma degree in mineralogy at the University of Cologne and got his PhD from University of Stuttgart while working in the Department of Rabenau at the Max Planck Institute for Solid State Research. As a fellow of the German National Merit Scholarship, he benefited from an opportunity of a research stay at the Bob Vaughan Group at California Institute of Technology. And then later, the Max Planck Society Award for the best PhD thesis, known as the Otto Hahn Medal, allowed him to join the Massachusetts Institute of Technology as a visiting scientist between 1983 and 84. This period was also part of his postdoctoral activities at the Max Planck Institute for Solid State Research in Stuttgart, which were mainly concerned with his research on alkaline ion conductive framework structures. Later, he actually moved to industry. From 1986 to 1992, he built a research group for the development of chemical sensors at the Swiss-German company Andresen Hause. And in 1992, he rejoined the Max Planck Institute for Solid State Research again, and where he assisted Joachim Meyer in building his new physical electrochemistry department. Klaus-Dieter Kreuer is also lecturing at the University of Stuttgart since 1990, where he received his habilitation degree in 1999. His research interests were always centered around the investigation of the formation and mobility of hydrogen-derived defects in condensed matter. The focus of his research covers both a better understanding of fundamental issues and the development of novel materials for specific applications. His work comprises a myriad of experimental and theoretical techniques in organic and organic synthesis, characterization by X-ray diffraction, neutron diffraction, nuclear magnetic resonance, electrochemical techniques, and of course, computer simulation. Klaus-Dieter Kreuer has published about 110 papers, which attracted more than 25,000 citations, and he also holds 11 patents to his name. Among his many pioneering contributions to science are, of course, the elucidation of the modern picture and mechanistic aspects of proton conduction and Grott's mechanism in aqueous and non-aqueous systems. He also pioneered the use of molecular dynamics in solid-state ionics, the use of high magnetic field gradient NMR in solid-state ionics. He also contributed a lot in unfolding the complex relations between structure, morphology, viscoelastic properties, hydration behavior, proton and water transport in polyelectrolytes and ionomers, such as naphion. In recognition of his achievements in this field, I would like to transfer the microphone to Professor Aivaras Kareiva, the chairman of Theodor von Grott's Foundation.
Thank you very much, Linus. So it's a big honor for me to announce on the behalf of Theodor Grott's Foundation what Dr. Klaus-Dieter Kreuer was awarded of Theodor von Grotus Medal for his important contribution in understanding the proton conduction and the Grotus mechanism in different materials. Thank you very much for your research, Klaus-Dieter Kreuer. Thank you very much. And you, I hope you will find this medal in your envelope.
Well, this is really a surprise. I really was prepared for a lot of things, but not for that. So let me open the envelope. Wow. Well, I think this I have to show to the students. Can you see this?
Yeah.
Wow. This is a big surprise. No, really, thank you very much. I think I have to come back to this later after the presentation to respond to this and thank you again with a little bit more extensively. I think now time is really running. We already got 5 minutes. So I will start, but I will come back to you later and thank you again. Okay, so let's start. Yeah, thank you, Linus. Well, you really struck me with this. I suppose this is the first presentation just after the lunch break, if I understand the program correctly. And Linus and me, you may remember, for Linus and me, this was always the time to go into into our scientific exchange just after lunch, usually with a cup of really strong coffee. I hope you had a good lunch and you have made yourself comfortable with a cup of coffee, maybe even with a little piece of chocolate. Why this is important, I hope you will understand in a couple of minutes, and you are ready for 1 hour of scientific exchange. Well, in fact, I would like to introduce hydrogen as an energy carrier by a few very basic considerations about energy density and conversion efficiency. And I sincerely hope that there are a few points which are surprising, even for those of you who have a background in thermodynamics and electrochemistry. After this 200 years of history, this is for your entertainment, but also to make you a little bit proud, because the science behind really started in your country. And the name was already mentioned. It was Theodor von Grotus, which you just saw on this medal. Finally, I would like to make a few points about ongoing activities, mainly focusing on the research we are doing in Stuttgart. And this is mainly on proton and OH- conducting membranes. Okay, I suppose all of you have a kind of idea how much electrical energy can be stored within a lithium-ion battery. This is around 200 watts per kilogram. But you probably don't know how much energy is in this bar of chocolate. I hope you can see this. You know, I took a photograph, which you see on the screen as well. Well, this is much more, 30 times more, about 6.4 kilowatts per kilogram, because this has to do with the fact that chocolate is a fuel. You can harvest this energy just by eating the chocolate, or you can just burn it in air. In both cases, you need oxygen to get the energy out of the chocolate. And of course, the oxygen is not included in this mass energy density. And this is, at least to some extent, the reason why this number is so high. Well, here you see the energy density of other fuels like wood, alcohol, diesel. And you are probably not surprised that hydrogen is the fuel with the highest energy density when you burn it according to this well-known reaction. Even if you include the tank of the hydrogen into the balance, the energy density is still an order of magnitude higher than this of a lithium-ion battery. Well, moreover, hydrogen can be produced from renewable energy just by using electricity produced by solar or wind and doing electrochemical water splitting in such an electrolyzer. You can use the hydrogen in a fuel cell actually to get back the electrical energy, and the availability of both technologies actually in principle allows us to couple the sector of energy production by renewables to the transportation sector, where the electricity could be used to run cars, trucks, or even trains. This looks all very good, but as always, there are also some downsides to the hydrogen, and this has to do with the conversion efficiency of fuel cells and electrolyzers. I mean, if we were able to operate fuel cells and electrolyzers close to thermodynamic equilibrium, and this would be at a potential of about 1.2 volts, which corresponds to the free energy of this reaction. Well, I have to remove this, okay. Which is a little bit less negative than the heat of reaction. And this has to do with the fact that the entropy of this reaction is negative, which is due to the fact that 3 molecules, 1 hydrogen or 1.5 molecules, 1 hydrogen and half an oxygen molecule form just 1 water molecule. This usually corresponds to a negative reaction entropy. And the energy which can be harvested from a fuel cell under reversible conditions is identical to this free energy. And if we just define the efficiency, which is in fact the efficiency limit in this case, as the harvested energy compared to the heat of the reaction, then this would be like 94%, which is definitely more than the efficiency defined by the Carnot cycle, which is limiting the efficiency of a heat engine. Well, there are even reactions which have an efficiency more than 100%. How is this possible? I mean, if the entropy is positive, and this is actually the case for heavy hydrocarbons or for solids such as carbon, then delta G actually can be more negative than delta H. And this reaction was actually used in a fuel cell by Bauer and Preiss in Switzerland in the 30s. And of course, they were not able to harvest the full free energy. But in principle, and there's no thermodynamic argument against this, the limiting efficiency of this fuel cell should be 163%. Well, now you may ask the question, well, is this possible thermodynamically? What's about the first law of thermodynamics, which demands energy conservation? For this, you have to understand that an electrochemical device, such as a fuel cell, is an open system which can exchange heat with the environment. So principally, it should be possible to extract heat from the environment to convert this heat into electrical energy, and in this way the efficiency would be more than 100%. So there's nothing wrong with thermodynamics. Well, of course, in practice, you never obtain more than 100%. And the question more is the efficiency higher in practice than the efficiency we know from heat engines, which are limited from the Carnot cycles. Okay, a realistic energy efficiency for a PEM fuel cell, in fact, is around 50%. And you can nicely see where the losses are from this current voltage curve. First of all, the open circuit potential of a fuel cell, a PEM fuel cell, is far below the thermodynamic potential, which is about 1.2 volt. And this has to do with the fact that the oxygen reduction reaction at the cathode side is usually quite sluggish, and it needs some activation through lowering the potential. So we already lose like 20% right at the beginning, but then there are additional losses, mostly due to the ohmic resistance of the system. This is essentially determining this regime, and at high current densities, there are even transport limitations. The gases have to be transported to the site of reaction, and the reaction products have to be transported away. These are all losses. And there's also a little bit of gas crossover through the membrane of oxygen and hydrogen, which is then also lost for the reaction. But what we also nicely see in this current voltage curve is that the power you can take out of a fuel cell is actually really high. I mean, it's in the range of up to 2 watts per square centimeter. If you compare this to the power of a lithium-ion battery, which is in the range of milliamps, this is almost like 3 orders of magnitude more than that. This small short stack, which was actually produced by PowerCell and which is licensed to Bosch, produces 10 kilowatts. And actually the fuel cell stack is only this little bit. This is about 1 or 2 centimeters, and this produces like 10 kilowatts. So the power density is extremely high, but the efficiency of the fuel cell is about 50%. Well, the same actually applies to electrolysis. Typical electrolyzer operation modes are in the range of 1.8 volts power at a current density of 3 amps. Now, if you compare this to the 0.6 volts at which usually fuel cells are operated, that's a good compromise between power density and efficiency. Then you see that the hydrogen, which initially has to be produced by electrolysis at a potential of 1.8 volt, is used in a fuel cell, where at the end only 0.6 volts are left. So we kind of lose 2/3 of the potential. So the efficiency, if you wish, wheel to wheel, is about 1/3, which is only half of a battery, which is about 2/3. So we always have to keep in mind, if we go for hydrogen as an energy carrier, we need about twice as much renewable energy to get about the same energy, at the end of the chain. Okay, let us move on to a time where energy or conversion efficiency was really not the big issue. As soon as the first batteries were available, they were produced by Volta in Como in 1800. The electrical energy which was available was immediately used to do water splitting. It's really amazing to see, from this historical picture, that in these first experiments, these people recognized that only half of the oxygen twice as much hydrogen is produced compared to oxygen. This is really interesting. It actually took more than 40 years that Schönbein tried to reverse this process, and he actually published a paper on reverse electrolysis. And this was actually the same in the same year William Groove did in England. His background was development of new batteries, And he presented something he called a gas voltaic battery, which is essentially a fuel cell. You know, he just used test tubes filled with oxygen and hydrogen, and he put wires inside. Everything was immersed in sulfuric acid, and he could demonstrate the formation of a potential. Today, Schönbein and Groove are considered to be the fathers of the fuel cell. But now really coming to Theodor von Grotius, the science behind really started by a very deep thinker. That's at least my opinion. Grotius actually thought about this water electrolysis, and he asked himself the question, how is it possible that electricity, he calls it électricité galvanique, the language in science at that time was actually French. How is it possible that hydrogen and oxygen form at different locations in space? I mean, if just the electricity splits the water, then both gases should be formed at the same point in space. And to resolve the problem, he actually had really an amazing idea. Grotius' idea was that there is permanent decomposition and recomposition in water, even in the absence of an electric field, we would say today. And the idea was that this is happening on closed trajectories. He is actually using the term circle. And this is why we don't see any of this from looking at the cell from the outside. And because each decomposition step is immediately followed by a recomposition step. Now, in the presence of an electric field, he thought that this circle actually open up and form a chain between the two electrodes of the system. The same process is still going on, but of course, at the end, you know, this positive particle, which is reaching the cathode, doesn't find a partner to recombine with, and then evolution of hydrogen is observed, and on the other side, evolution of oxygen. Well, in fact, my feeling is that what Grotius described here is already something like what is described by the Nernst-Einstein relationship, telling us that both diffusion and conductivity are processes which are the consequence of the same elementary reaction, which he described as decomposition and recomposition. Well, here you see the equation again, and today we know that diffusion is a thermally activated process in solids and liquids over barriers. And if we just take this one-dimensional picture with these barriers, with the barrier heights of delta H, the probability for a particle to jump over the barrier is given by this Boltzmann term. And of course, the probability for a forward reaction and a backward reaction, you know, in this one-dimensional case, are identical. Well, this is tracer diffusion, if you wish. In the presence of an electric field, there is a slight bias because in the direction of the field, the barrier is slightly reduced, and in the opposite direction, it's slightly increased. Well, therefore, there is a kind of net flux of particles, which is just the difference of these two exponentials. You know, in this one, the barrier is a little bit reduced, and there the barrier is a little bit increased. And as you all know, the difference of two exponentials is a hyperbolic sign, which you see on the next slide. This is a hyperbolic sign. At very high potentials, this merges into one exponential, and that on the other side, it actually merges into the other exponential, but for slow perturbations. And they are slow when you measure the conductivity of water, for instance. You know, if you have 1 volt per centimeter, this is only about 10 to the minus 8 volt for the distance between 2 water molecules. So this is really small compared to the barriers, which are in the range of several hundred millielectron volts. So in this range, this is linear, and this is actually why ionic conductivity follows Ohm's law. But it's essentially the situation described by Grotus. Well, at the same time the Nernst-Einstein relationship was formulated, it was also known that the diffusion coefficient, which is related to the ion mobility, is also related to the viscosity of the medium. This is quite obvious. The more viscous a medium, the lower the diffusion coefficients of particle dissolved in this medium. And at the same time, or at the beginning of the 20th century, it was already possible to measure all these parameters. So conductivities could be measured by measuring currents and potential differences. And all these relationships were actually confirmed experimentally, which actually means that the mobility of most ions in aqueous environment fall into a very, very narrow range. The only exceptions are the protons and the OH minus ions. And researchers immediately recognized that this has to do with the fact that the proton may exchange with protons from the solvent, simply because this was only observed in solvents like water and alcohol, but not for aprotic solvents. There, this phenomenon was not visible. And I think this was a very good idea, which still holds for the models today. But there was one misconception at that time. The idea was, well, if a proton actually exchanged with a proton of a water molecule, and another proton of the water molecule is actually protonating the next water molecule, then the proton doesn't have to travel this distance. You know, in the literature, they call this Wegverkürzung, and the other expression is Scheinleitfähigkeit. In English, it would be something like a seeming conductivity. And this misconception is actually, you still find today in textbooks of physical chemistry. I will come back to this in a couple of minutes. Another misconception was actually by Hückel, the famous Hückel from the Debye-Hückel theory. Obviously, he was very much inspired by his own theory on electrolytes, aqueous electrolytes with water as a solvent with a high dielectric constant. Well, the assumption was that the water molecule has a dipolar moment, and Hückel assumed that also the hydronium ion is just a protonated water molecule, which also has a dipolar moment. And his idea was that in the presence of an electric field, this dipole is biased towards the next water molecule, to the negative end of the next water molecule, with a preferred transfer of protons into this direction as compared to the direction opposite to the electric field. Well, this is actually wrong in two ways. First of all, the hydronium ion actually doesn't have a real dipolar moment. It's almost there's almost no dipolar moment. The other thing is that the hydronium ion is actually strongly bond into the water structure, and there's very little dynamics of the hydronium ion. But this Hückel could not know at that time. Well, another really cool, you probably would say cool misconception is proton tunneling. I mean, you all know that the big days of quantum mechanics, or when everything started, was in the 1930s. And during this time, also after the war, there were a few people who tried to calculate tunneling probabilities of the protons to potentials like this. And this is supposed to be the potential the proton sees between two water molecules. And they actually found very high tunneling matrix elements, suggesting really tunneling to explain the high mobility of protons. The problem with this picture is actually that usually the potential is not symmetrical. As we'll again see later, the proton undergoes tremendous self-localization, which is usually making these potentials very asymmetric. And we'll even see that in most cases, there is no barrier and the transfer is usually adiabatic. Interestingly, even Eigen, which is very much known for investigating very fast reactions, experimentally, he assumed that the proton is completely delocalized between the hydronium ion and the first shell of hydration. Well, the whole thing is actually called the Eigen ion. This is definitely not true. After the war, you find a lot of static pictures like this. Chains of water molecules in which protons transfer in a kind of cooperative way. And in fact, this kind of reminds me this very early word from the 20th century with a seeming mobility. And what the authors actually, even at that time, did not clearly see that this transfer along a hydrogen bond chain only polarizes the hydrogen bond, but it's not real proton conductivity, because once the chain is polarized, it's not ready to pick up the next proton for transferring the charge here from the right to the left. And this was clearly recognized by Hans-Georg Hertz in 1982 or so. He clearly stated that there must be bodily transport of protons. There's nothing like a seeming mobility, and this must be along uninterrupted trajectories. And this transport of protons must involve not only the transfer of protons from one molecule to the other, but it also involves the reorientation of this water molecule. In fact, this defines very nicely the problem of proton mobility in general. For this, let us consider the thermodynamics of this simple molecule. You know, these are two water molecules. Wait a minute, my mouse there's some trouble with the mouse. Oh. What is happening here? The mouse is moving back and forth. Okay, I just keep on going. This is the a hydrogen bond between two water molecules. And what you see on this plot is actually the bond energy, which is this curve. And this is the barrier for proton transfer as a function of the do you see the screen?
No. Oh, now we see.
And then there is, I don't know, the system is not responding to the mouse. You know, this is not nice, because I really need the mouse. Okay, so the proton, the hydrogen bonding you actually see here, which is really high for the so-called Sundel ion. In fact, I met Sundel in Lithuania in Bristonas. I don't know whether the pronunciation is right. In 1995, when you guys actually organized an international conference on horizons on hydrogen bond research, and actually found an old photograph which is showing Zundel, which is actually giving the name to this kind of ion. And as you can nicely see, this bond is really very strong. And if you stretch the bond, this bonding energy is going down, but at the same time, the barrier for proton transfer is going up. And there's actually no oxygen separation at which both energies are low. I mean, proton mobility in water has an activation enthalpy of only 0.1 electron volts, and this is 1 electron volt. So we cannot explain proton mobility just by considering a few water molecules. For this, we really have to consider extended ensembles, and this really is the clue for understanding the transport of protonic charge in aqueous environment. This is the Zundel ion in a water structure, and in fact, the equilibrium bond length is below 2.5 angstroms. This really corresponds to an extremely short hydrogen bond with almost no barrier. But already in the second hydration sphere, the bonds are like in normal water, around 2.7 angstroms, which allows easy breaking and forming. And this bond has almost no barrier, which allows proton transfer. And the interesting thing is that the bond breaking and forming in this part of the structure and the transfer of protons within this Zundel ion, they are highly coupled, as you can see in the mechanism, which was actually first described by Mark Tuckerman. Again, here you see the Zundel ion, and if an additional hydrogen bond is formed with this oxygen, this incoming charge will actually push this proton more towards this oxygen, and an eigenion, a hydronium ion, is actually formed. And when another hydrogen bond on the other side is broken, this is actually moving this proton from this side to the other side. At the end, the Zundel ion has actually moved to this position, and this is actually the elementary process. And as you nicely can see, from the potential of the proton in the hydrogen bond, in the Zundel situation, there's almost no barrier, and the effect of the hydrogen bond formation here is actually a change of the shape of this potential from this potential to this potential, and this is naturally pushing the proton from one side to the other. Well, this molecule has virtually no dipole or moment. This is also true for the eigenion. This Hückel could not know, and because the hydrogen bonds in which the transfer takes place are so short, we don't have to consider tunneling. Tunneling is really not important in this mechanism. But what is important is the fact that in this elementary step, the proton, which coincide with the location where the protonic charge is, and the protons in the water molecules, they exchange on the picosecond time scale in this mechanism. Therefore, there's nothing like fast protons you could detect, but still the protons are decoupled from the hydrodynamic background. So there must be bodily transport, as stated by Hertz. And this is something we tried to measure 30 years ago. I mean, this is a paper I'm really very proud of, simply because of the experimental achievement. We measured the diffusion coefficient of protons and of oxygen in hydrochloric acid as a function of molarity. And you can clearly see that for like 5 molar hydrochloric acid, the proton diffusion is really about 4 to 5% higher. This is the ratio. And these are the data points. And this is, so to say, what we expect theoretically if all protons are, so to say, mixing. So you really can see the very high proton mobility, which is 5 times higher than this of water, in the average proton diffusion coefficient, which can be a couple of % higher than the hydrodynamic background. Well, one other thing you have to keep in mind is that this mechanism, which is the Grotus mechanism, essentially, it's also called structural diffusion, is only observed in dilute acid. As soon as the concentration is higher, and we see this also in hydrochloric acid, all the charges bias the hydrogen bonds, which reduces the local symmetry, which is so important for this mechanism to happen. And then this mechanism dies out. And what is actually left at very high concentration is just what we call the vehicle mechanism, which is just the diffusion of protonated water molecules and the back diffusion of unprotonated water molecules. And this is also something which is happening in the membranes, which are used in fuel cells and electrolyzers. Well, now coming to some current activities on membranes. This is the last part of my presentation. Membranes used in fuel cells and in electrolyzers, of course, they have to show high proton or OH- conductivity. This is actually needed to, so to say, mediate the electrochemical reactions taking place at the 2 electrodes. At the same time, these materials have to separate oxygen and hydrogen. So they have to be gas tight. And of course, they have to be stable, especially electrochemically stable under the really harsh conditions, reducing conditions on the anode side and very oxidizing condition on the cathode side in the fuel cell. And the material which is really doing this is called naphthion. Linus has mentioned this. This is a little bit the result of a forced marriage, if you wish. Naphthion is a so-called ionomer with a Teflon, very hydrophobic Teflon backbone. There are these side chains, and they are terminated by the superacidic sulfonic acid group, which is really a superacid in this case. And this gives it, makes it extremely hygroscopic. And in the presence of water, of course, these sulfonic acid group, they are hydrated and they want to separate from this hydrophobic polymer. And this gives rise to some ordered structure, which shows up in the X-ray as a so-called ionomer peak. You know, this is Q. This is inverse space. But the thing is that everybody believes in this phase separation, but there's still a debate about details of the morphology. I mean, about 10 years ago, we had a conference where different models were presented. Well, I don't want to go into this debate. I just would like to show what we think the morphology of naphthion is. Well, of course, the position of this ionomer peak moves to smaller Q with increasing hydration. So the correlation length is increasing as a consequence of swelling. And in fact, we did this over we measured X-ray over a wide range of water volume fractions. So these are all data points which scatter a little bit, but if you really cover a wide range of water contents, you clearly see that the correlation length increases with water volume fraction in a linear way. And this is immediately telling us that the swelling of the structure, at least locally, is only in one direction, which immediately implies that the structure must be locally flat. So the water in these membranes and also the conducting protons, they are forming highly tortuous films, and it's within these films of a thickness, this is actually the film thickness here, and this is a typical water content in a running fuel cell, and there you see the film thickness is about 1 nanometer. Within this nanometer film, all the transport takes place. Well, here you see the morphology in a more realistic way. Here you see the sulfonic acid groups terminating the polymeric aggregates, and this is the water. And it's within this ionic aqueous domains in which all the transport of protons, of water, but also of gases takes place. Just let's have a look of the proton mobility in Naphion as a function of the water content. This is volume fraction. This is in terms of hydration number, which is the number of water molecules per sulfonic acid groups. This is pure water, by the way. Proton mobility is 5 times higher than the water diffusion coefficient. In Naphion, at full hydration, which is about 20 waters, it's still about a factor of 2 higher, but you also can see that with decreasing water content, proton mobility is merging into the diffusion coefficient of water. So at low water content, let's say a little bit below 50% relative humidity, we clearly see only transport of protons by the diffusion of water, which is essentially the vehicle mechanism. But from this, it's already clear that if we want to increase the conductivity, and this is always good for these applications, we have to increase the water tracer diffusion coefficient. And this can be done by increasing the ion exchange capacity, because the more ionic groups are in the membrane, the higher the water content at a given relative humidity, because the ions are actually binding the water. And IEC, of course, ion exchange capacity, also helps to increase the concentration of protonic charge carriers. So this really should increase the conductivity in 2 ways. And this is actually why we are moving away from Naphion, which has an ionomer with this architecture, main chain, side chains, and this essentially under the bottom line gives you relatively low ion exchange capacities, close to 1 milliequivalent per gram. So we are actually moving on to hydrocarbons, where we can put the charges directly on the backbone. And well, in our laboratory, we actually decided for these polyphenylene sulfones, which are really extreme polymers. This is the repeat unit. It's just a polyphenylene, and all the phenyl rings are connected through these SO2 groups, which have a very strong minus I effect. So they really take electron density out of the ring, and they are a little bit negative. And this electron density reduction of the aromatic ring actually stabilizes this bond against hydrolytic attack. And moreover, it's making this sulfonic acid group also a superacid, which is important to obtain high conductivity at low relative humidity. So all the chemistry we are doing at the moment in our laboratory is based on this polymer. Of course, there are modifications to get rid of brittleness, to reduce swelling, to make the polymer a little bit tougher, but it's essentially this molecule. Well, I also would like to share with you this result, which I found quite interesting. You may say, well, so let's pack as many sulfonic acid groups as possible on such a polymer. And we had a co-worker, Jogo Takamuku, who actually was able to do an octasulfonated biphenyl, which really has an extremely high density of ionic groups, but the conductivity is actually lower than the conductivity of this or this polymer. And this actually has to do with the onset of Manning's counter-ion condensation, which is an electrostatic effect. So for our further research, we are actually making polyphenylene sulfones, between these 2 compositions. And with our partner in industry, which is a small company close to Stuttgart, we are able to make membranes out of these materials by casting, conventional casting. Interestingly, these polymers are soluble in aprotic solvents such as DMAC or DMSO, and we actually can spray coat these membranes onto the electrodes directly. And of course, this allows us to make very thin membranes, thinner than 10 micrometer. And even for very thin membranes, these membranes have very high conductivity and very low gas transport, which is especially important for electrolyzer applications. Well, you've seen this graph
10 minutes,
already.
Klaus-Dieter.
Yeah, I'll make it. I'll really coming to the end. This is the current voltage curve of a fuel cell with such a membrane, and you see current densities up to 8 amps per square centimeter can be achieved with very thin membranes, which are below 10 micrometer. In electrolyzers, the big advantage is actually the very high conductivity of these membranes. Well, here you see a current voltage curve of a conventional electrolyzer using naphthion, typically operating around 2 volts at a current density of 3 amps. With the hydrocarbon membranes, we were actually able to reduce the potential to 1.7 volts or so. And at the same time, the gas crossover is heavily reduced. You know, this is a crossover. This is a data point from our membrane, and this is the naphthion point. So let me move on to one current hot topic with a few slides, and this is actually the promise of OH- conducting membranes. I mean, the reason why there is a tremendous interest in this is because this allows us to move away from noble metal catalysts, which have to be used in PEM fuel cells, because these catalysts are the only ones which do not dissolve under these very acidic, environment. In electrolyzers, even iridium oxide has to be used on the anode side, you know, and of course, this is pushing the costs. In the case of OH- conducting membranes, one should be able to use catalysts such as nickel or silver on the air side. These ionomers, OH- conducting ionomers, usually have quaternized ammonium ions as positive charge on the backbone, which are, so to say, charge compensated by the OH- ion. The problem with these membranes actually is that the OH- is an extremely strong nucleophile, which is attacking this positive charge by Hofmann elimination, you know, at this beta proton, or just by a substitution reaction. And there are virtually no stable membranes available at the moment. And one of our PhD students, Michel Marino, he actually looked into other cations for these ionomers. And he actually identified these spirocyclic cations, which show much higher stability under really severe conditions, but they are in fact not enough stable at the moment. We even made the polymer, which is rather stable, but in a fuel cell or electrolyzer, they really have to operate over several thousand hours, and this is not possible yet. So at the end, of course, I really would come to something which is related to the work of Linus. I think I have to do this, and this is actually relating to high temperature PEM fuel cells, which operate at temperatures of around 160 degrees centigrade. They use PBI, polybenzimidazole membranes, which actually contain a lot of phosphoric acid, and all the conductivity in these membranes actually relies on the high conductivity of the intrinsic proton conductivity of neat phosphoric acid. And this is actually something Linus looked into. And Linus actually told me that he was born in Uniskis, which is close to the border in your country, which is only 10 or 20 kilometers away from the birthplace of Theodor von Grotius. Wow, this is really something. Okay, coming to phosphoric acid. Phosphoric acid is really unique. I mean, I've shown to you this picture of proton diffusion compared to oxygen diffusion in aqueous environment, you know, and there's, you nicely see the decoupling of the proton from the hydrodynamic background. In the case of phosphoric acid, proton diffusion is about 6 times faster than the diffusion of the phosphate itself. So there, the proton is really very efficiently decoupled from the dynamics of the hydrodynamic background. And the reason for this, or at least part of the reasons for this, is the hydrogen bond structure of phosphoric acid. And this is the phosphoric acid molecule with 1, 2, 3, 4 oxygens. 3 are protonated, and they can act as a proton donor in the hydrogen bond network. There's only 1 oxygen which is not protonated, and this oxygen can accept at the most 2 hydrogen bonds. So if you take many of these molecules and form a hydrogen bond structure, there are always protons as part of an OH group which do not find a proton acceptor. So if you think about a proton conduction mechanism, you have learned that we have to break and form hydrogen bonds, and that we have to transfer protons from one oxygen to the other. And this is a process in the case of phosphoric acid, which takes about a picosecond for breaking and forming a hydrogen bond. But there are a lot of OHs which are not involved in hydrogen bonding, and just the formation process is very fast. It's about 2 orders of magnitude faster than the breaking and forming process. This is just hydrogen bond formation. And this is actually part of a mechanism which was discovered by Linus. And if you are really interested to understand the full mechanism, I mean, Linus is around the corner, just ask him. I'm sure he will be happy to explain to you the full story. Well, at the end, I would like you to keep in mind that hydrogen as an energy carrier really would enable us to couple sectors: the sector of producing electrical energy from renewables, the sector of transportation, but also the sector of making steel or chemical industry. Hydrogen has the advantage that it really has a very high energy density. The problem is a little bit conversion efficiency, which is really kind of low. So we really need a lot of renewables, you know, to make the hydrogen economy happen. And I think there are a lot of things, technical problems, which still have to be solved. You know, we are working on this here in Stuttgart, and I'm sure there will be times of frustration, but we always should keep in mind that for this we have another fuel, and this is chocolate, and I'm pretty sure this will help us against frustration. Finally, I would like to thank the 2 PhD students I'm working with at the moment. This is Andreas Münchinger and Tom Saatkamp. And this picture was actually taken like 2 years ago on the occasion of the inauguration of a hydrogen filling station, which is only 5 kilometers away from our institute. You see, we are already doing the first step. Thank you to the PhD students, and thank you to you for listening. And of course, feel free to ask any question. Thank you.
Thank you, Klaus-Dieter. Let's applaud the speaker. And do we have any questions from the audience? From YouTube? Can the moderators update on that? So before we get get the first questions in, let me ask a couple of questions. So how much is a problem in the hydroxide exchange membranes, the fuel contamination?
You mean OH minus conducting membranes?
Yes, in the case of OH minus conducting.
And what do you mean?
Is that a problem?
What do you mean with contamination?
By water vapor.
By water vapor. Water vapor is actually needed to make the OH minus membrane conducting. You need water, like in the case of a PEM membrane. Locally, the mechanism is like OH minus conductivity in aqueous environment, that it also involved proton transfer from the water molecule to the OH minus. But there are contamination problems, and this has to do with the fact that fuel cells operate in air, which has a lot of CO2, which is actually acidic and reacts with the OH minus, forming bicarbonate. But you can actually absorb the CO2 in kind of filters, and you can use so-called purging. You have to keep in mind that the OH minus is produced at the cathode, and when the current is high, this OH minus is actually purging the CO2 out of the membrane. So at high current density, in fact, you can live with CO2. But contamination is always a problem. I mean, if you operate fuel cells, I mean, there are other gases which actually neutralize the membrane. In an electrolyzer, there may be really small amounts of ions which ion exchange with the proton. I mean, contamination is a problem, but there are fuel cells around which operate thousands of hours if you take care of these contaminations.
We have a question from the audience, Benediktas Brasiūnas. What about the storage and safety concerns for using H2 as a fuel?
Well, I mean, of course, everybody has this picture in mind of the burning Hindenburg, the Zeppelin, which burned. But in this case, actually, what you saw burning was the aluminum coating of the Zeppelin. I mean, here in Germany, we have the TÜV, the Technische Überwachungsverein, and they actually have been doing all kinds of tests. The thing with hydrogen is, as long as the hydrogen is not indoor, if you are outside, it's so light that when a tank bursts, the hydrogen is immediately going up. And only in this process, it's diluted with the oxygen before it actually can reach the limit where it can explode. And usually it starts burning like 7-8 meters above. So if you are outside, there should be no problem. I mean, there are a lot of tests which are showing this.
We have another question from Svajos Osodauskas. Would it be easier or more difficult to achieve better efficiency if heavy water D2O was used?
This is really a good question. Well, in fact, heavy water has a lower water diffusion coefficient. And as you know, proton mobility is related to the water diffusion coefficient. And the transfer rate actually in the Sundel ion is a little bit enhanced. But these are minor effects. But if you are a snob and if you have enough money to operate your fuel cell with D2 and D2O, I mean, you can do this, but there is no point in that. Absolutely not.
I have another question, I think, which would be interesting for students as well. What is your opinion about hydrogen as a ion carrier in closed systems, as if in batteries, like we have lithium-ion batteries,
okay,
sodium-ion batteries? What do you think are the general problems, advantages, disadvantages of using proton or hydrogen as a carrier, as a charge carrier in a closed system?
Well, in a closed system, you actually need an anode and a cathode in which the proton then finds different chemical environments which are defining the potential. And we have discussed this issue earlier. I mean, you sent me a couple of papers 2 years ago, and the energy efficiency is actually very low. And if the system is aqueous, also the thermodynamic potential window in which you can operate an aqueous electrolyte is only 1.2 volts or a little bit higher. So under the bottom line, the energy you can store is at the moment lower than for lithium. I mean, you never know. If you think about storing huge amounts of energy, and if you not talk about mobile application, you may keep this in mind. Then we also talk about things like redox flow batteries. But if you rely on high energy and power density, which you need for transport applications, at the moment, there's no way around lithium. Even if we talk about sodium batteries, I mean, the loss of 20–30% of power and energy density is not acceptable for mobile application. But I mean, we are doing research. I mean, we should look into these systems, but it's not like that there is a good chance to find a solution very soon.
Okay, thank you very much, Klaus-Dieter. I got the information that we have to move on to the next session, to the poster session.
Okay.
One more question in the chat, but I think we have to leave it for email exchange or something like that. Thank you very much once again.
Well, thank you for listening.
I'll talk to you later. Bye.
I will talk tonight, right?
And please show once again your award.
Ah, sure. Can you see it?
Yeah, perfect.
Thank you so much.
Thank you.